So today, continuing to our last discussion about these semiconductors. So today we are going to discuss the types of semiconductors. So whenever a semiconductor is in its pure form, whenever a semiconductor is in its pure form, these are called as pure semiconductors, or another term we can use here is intrinsic semiconductors. Intrinsic semiconductors. So these intrinsic semiconductors, the electrical conductivity of these intrinsic semiconductors, it highly depends on temperature, and it cannot, these, the devices manufactured by these intrinsic semiconductors cannot be, are not practically, uh, we cannot fabricate these devices. So the conductivity of these semiconductors can be enhanced in terms of magnitude, and we can reach any desired value by and make it independent of temperature by doping certain impurities, by doping the intrinsic semiconductor with certain impurities. So whenever we dope here, doping means addition of impurities. Whenever the addition of impurities occurs to an intrinsic semiconductor, the resultant we call it as extrinsic semiconductor. So the resultant we call it as extrinsic semiconductors. So now in these extrinsic semiconductor, the essential feature of these extrinsic semiconductor is that the electric current in these extrinsic semiconductor is highly voltage dependent, and the temperature dependency of the electrical conductivity is much lesser in these extrinsic semiconductors. And one more important thing here is the electric current. The electric current is transported by two different charge carriers. The first one is electron and the second one is hole. The first one is electron and the second one is hole. And these extrinsic semiconductors, are the one which are used in certain solid state devices. So whatever the semiconductor we use in the solid state devices are extrinsic semiconductors. So these extrinsic semiconductors are, again, these are of two types. The extrinsic semiconductors are of two types. Types of extrinsic semiconductors. So we can list it out as N-type semiconductor and P-type semiconductor. So these N and P type are defined by the kind of impurity added to a intrinsic semiconductors. So first we shall discuss about this N-type semiconductor. N-type semiconductor. A N-type semiconductor is obtained whenever a pure semiconductor is doped with a pentavalent impurity. So pentavalent impurity indicates that there are 5 electrons in the last orbit. That means there are 5 valence electrons. Right? So what actually happens here, if I try to represent it in a diagram, I shall consider the pure semiconductor as a silicon. So I'll just try to draw here. There are silicon atoms. So as we all know, silicon is a tetravalent material. Silicon is a tetravalent material. Tetravalent indicates that there are 4 valence electrons. So every silicon atom here has 4 valence electrons. Now we are going to introduce here an impurity such as phosphorus, which is a pentavalent material. So this phosphorus, it takes the position of any of the silicon atoms. Then in place of silicon we have phosphorus. This phosphorus has 5 valence electrons, 1, 2, 3, 4 and 5. So the 4 valence electrons form covalent bond with the remaining silicon atoms as shown here. But one valence electron is left behind, and even a small amount of thermal energy is sufficient to make this electron jump to the conduction band. So like this, an electron is in the conduction band without any production of holes. So electrons are the majority charge carriers in N-type semiconductors. And due to the intrinsic property of the material, holes will be there. So the holes are the minority charge carriers. So this is about N-type semiconductor. Similarly, now we shall study about P-type semiconductor. So the second type of extrinsic semiconductor is a P-type semiconductor. So this P-type semiconductor is obtained when a pure semiconductor is doped with a trivalent impurity or a trivalent material. So we shall understand this by again an example. I'll consider again silicon having 4 valence electrons. Every silicon atom has 4 valence electrons. So if I replace any of the silicon atom with the help of any trivalent impurity such as indium has 3 valence electrons. I shall replace this silicon atom with the help of indium. What can we get? Indium having 3 valence electron, and there are still more silicon atoms surrounding these. So the 3 of the indium valence electrons will form covalent bonds with the rest of the silicon atoms. but one hole is created, that is the deficiency of the electron. So this hole is even a small amount of thermal energy, even a small amount of thermal energy can make this hole move in the valence band. So here a hole is created, without any uh, without any vacancy created by an electron. So here the holes are majority charge carriers. Holes are majority charge carriers, and electrons electrons will be there due to the intrinsic property of the silicon atom. Electrons, these are called as minority charge carriers. These are minority charge carriers. So these are the types of semiconductors.